Okay, so today we're going to continue talking about comparing two samples, and this time we're going to diverge from talking about means. So in the last two lectures, we considered comparing two groups where the subjects were matched prior to the design, prior to carrying out the experiment, and then we did a t-test to compare whether the means differed. Then we went on to do an independent sample t-test where there is no pairing. You just have a random sample from two different groups and you compare them and you're asking whether the means differ. But today what we're going to do is we're going to ask a different question, not about the mean, but rather about variances. So we're going to be comparing two groups, asking the question, is this for some characteristic, is one group more variable than the other or not? Okay, so we're comparing variances, not means. And it's actually quite a simple test to carry out, and it's useful in two contexts. The first context it's broadly useful for is comparing variances, and variances are often very important things to compare. For example, in plant and animal breeding, you need to have variability in the traits that you're trying to select for. In fact, there has to be a genetic basis to that variability. So variance is important unto itself. If selection is going to occur, artificial or natural selection, there has to be variability. So it's a very useful question to ask in many different biological systems. Is one thing more variable than another or not? The other context applies really to the independent sample t-test. There are two assumptions of an independent sample t-test. One of them is that the populations sampled for the trait of interest are normally distributed. But the second one for the independent or two-sample t-test is that the variances of the two populations are the same. So we can use the f-test we're going to deal with today to actually test that assumption, and then if we don't reject a null hypothesis, in other words, if there's no evidence the variances differ, then we can happily go ahead and carry out the independent sample t-test. So we're going to use this test really in two ways. To compare two variances, when that's the question that's inherently interesting, or to actually test the assumption of a two-sample t-test before proceeding with that t-test. And so the f-test rather for two variances is in chapter 12 on pages 347 to 349. The null hypothesis is of the form shown here, where you're just really asking whether or not, or the null is that the variances of each group are the same for the trait measured. And then we can have two-sided alternative as specified here, or there can be a one-sided alternative. Right? That one variance, in this case I said sigma squared 1 is greater than sigma squared 2, or the reverse, depending on the experimenter's prior knowledge or intuition, etc. You might have a one or a two-sided alternatives. There's really one assumption of the f-test, and that is that the populations sampled have a normal distribution for the trait. Okay, so then let's proceed, and I think the easiest way really to do this is just to do it by example, because it's a fairly easy test to carry out. So let's imagine we're going to compare two populations. We want to compare lizards. Whoops, sorry about that. We want to compare lizards. So it's the same species of lizard on two different Caribbean islands. But what we want to compare is how variable they are. Are they more are the populations more variable for some traits, say the width of their jaws, on one island versus the other? Okay. Jaws more variable, I'll just write down. And the experimenter didn't specify which island they might have more variable jaws on or not. So this is going to be a two-sided test. So the null hypothesis is always going to be that the true variance on island 1 equals the true variance of jaw width on island 2. And the alternative is going to be, in this case, it's a two-sided test, that the variances are not equal. So we're comparing two variances. And so you run out, you sample, take random samples of the whatever the lizard species is from island 1, and you do the same for island 2. And then what you need to do is estimate the sample variances. So we all already know how to estimate variances, right? The sum of the x's squared minus the sum of the x's all squared over n divided by n minus 1. So it's the same equation we always use for variances. So don't even bother to write that down, because you've by now should have that equation burnt into your brain. Anyway, for island 1, we randomly sample 10 lizards, measure their width of their jaw, and using those 10 data points, simply estimate the sample variance. So S1 squared, the variance of sample 1, ends up being 12.0. You go over to the other island, sample it. It's ideal, of course, always to have equal sample sizes because the tests are more powerful and it makes intuitive sense to have equal sample sizes, but you don't have to have equal sample sizes. So in this case, they managed to get 8 lizards, randomly sampled, measure their jaw widths, estimate the variance. So here the variance of the second sample, or the sample from the other island, was 14.0. So what we now need to do, and so this is, I should just say this is a two-sided test, as you can see from the alternate hypothesis. And the calculation of the test statistic, and the name from which this test derives, is called the F distribution. And so there's an F statistic you calculate. So I'll call it F calc. And for a two-sided test, it's really very simple. You simply you estimate the two variances, put the larger variance in the numerator, and divide that by the smaller variance, which you stuff into the denominator. Whoops, the smaller goes in the denominator over here. And it turns out that if in fact the variances are equal, then there's a theoretical distribution called the F distribution that predicts the outcomes or the distribution of what F should be. Right? So we're going to refer to yet more statistical tables, in this case the F distribution. Right, so the calculation is really simple. And so for this example, the F we're going to calculate, the test statistic, is simply the larger variance, which is 14 divided by the smaller. So it's 14.0 divided by 12.0, and that equals 1.167. So it's really a simple calculation. You just estimate sample variances for each of the two samples. You construct a ratio of sticking, for a two-sided test, sticking the larger variance in the numerator, the smaller in the denominator, and just divide it. So really probably the easiest statistical test we carry out. So now what we need to do is we need to look up the critical values of the F distribution. And to do that, we need degrees of freedom. And it turns out for an F test, there are two sets of degrees of freedom. Degrees of freedom associated with the numerator, I'll just call df num, and the degrees of freedom associated with the denominator, df denominator. And the degrees of freedom are easy to calculate. So the degrees of freedom for the numerator are just whatever the sample size of the numerator was. So we put 14 was the bigger variance, so the degrees of freedom are going to be a function of n2. So the degrees of freedom in this case are 8 minus 1, which equals 7. And the degrees of freedom for the denominator, so the denominator was the smaller variance, which was 12, and so the sample size there is 10. So here it's 10 minus 1 equals 9 degrees of freedom. And so what we need to do now is look up in the F tables the critical value of the F distribution. And so what we really want is the critical value of F with, so F critical with alpha 2, so that we have to look up in the right tables, alpha 2 equal 0.05, with first the numerator degrees of freedom, which was 7, and denominator degrees of freedom 9. So we're going to look this up. And I'll show you the F tables after I complete this lecture. So I'll show you how to look stuff up in these F tables. So we're looking up the critical value in tables with alpha 2 equal 0.05 with 7 degrees of freedom associated with the numerator, 9 with the denominator. And if you look that up, you find out that the critical value is 4.2. 4.20. All right, so let me sketch out what the F distribution looks like. So the F distribution is a distribution that looks like approximately like this. Remember, it's also a family of distributions that vary depending on the number of degrees of freedom. Here's 0 here, and you go out to positive infinity. And the F distribution looks something like this. This asymptote's down to 0. It might not look like that from my drawing. And with the F distribution, even though whether it's a one-sided or a two-sided test, we're always looking out at this tail of the distribution. And the reason we're always looking out here is, certainly it's clear for a two-sided test, we're always sticking the bigger variance in the numerator. And so this thing, right, we're always going to be looking out at this end of the distribution. And so we're going to put all alpha equal 0.05 under this tail of the distribution and find the critical value. So that's what I did. That's what I looked up in the F tables. As I said, I'll show you those later on, how you look things up in the F tables. Okay, so that's fine. So now we've got our sort of diagram where we've set up a rejection region out here, right, beyond 4.2, and a region of non-rejection, less than 4.2. So what was our F calc? Our F calculated value was 1.167. So that probably sits around here somewhere in the region of non-rejection. So we don't reject the null hypothesis. No reason to believe variances differ between those islands. So that's our conclusion. And so in this example, the experimenter was really only interested in, was legitimately interested in asking whether there's more variability of lizards on one island versus the next. But you would do exactly this test, this two-sided F test, if you really wanted to compare the means. One of the assumptions, the variances of the two populations sampled or two groups sampled are the same. So you first will do an F test, a two-sided F test, to see that you meet that assumption. Then, if you do meet it, in other words, you don't reject the null hypothesis, you then go on and do the test that would really be of interest, that is the independent or two-sample t-test. So that's the way another way in which we'll commonly use this test. But let me go on and do a one-sided F test. So in this case, someone wishes to test whether female mallards, so mallards are ducks, female ducks or mallards are less variable than male mallards. So male mallards. So males are expected to be more variable for some reason, whatever the biology there is. Females less variable. So that's sort of like the biology here for whatever the trait being measured is. And so the null hypothesis here is going to be, it's variances we're talking about, sigma squared female is equal to this variances of males for whatever the trait is we happen to be measuring. And the alternative hypothesis this time is one-sided, that females are less variable than male mallards. So you run out, you take a random sample of males, random sample of females, and you simply estimate the variance of whatever the trait is you happen to be measuring for both of those. So again, I won't give you the raw data, I'll simply give you the statistics that have been estimated. So the variances that we estimate for males ends up being 11.7, and the sample size for males, number of males, was 20. Sigma squared, the estimated variance for females was 6.3, and the number of females sampled was also 20. So a sensible experiment in using equal sample sizes. Now the departure, well, there's two sort of differences when you're doing this one-sided f-test. And here, it's the alternative hypothesis that specifies which variance goes into the numerator versus the denominator. So whatever is specified here as being bigger, so the null hypothesis indicates an expectation that males are more variable, males go in the numerator. Right, so the bigger one, the one that's supposed to be greater, goes in the numerator. So our f-calc is going to be the variance of males, because that's what is thought to be greater based on the experimenter's alternative hypothesis, and the variance of females is in the denominator. If the one-sided alternative was the other way around, then the females were expected to be greater, than the females would go in the numerator. So here you don't flip-flop the variances as a function of which is bigger after you estimate them. You're driven, you can write down what the f-calculator is going to be before estimating anything, based upon what is stated in the alternative hypothesis. And so in this case, we've got the variance of males, 11.7, divided by the variance of females, and you simply divide those, so it's trivial to calculate, and it ends up being 1.86. So that's fine. So now we need to refer to the F tables to get the critical value. And so note that the F tables actually span many pages. As I said, I'll show you some shortly. And there are different pages. So you have to refer to a completely different page of the F tables when you're doing alpha 1. So there's a set of pages for alpha 1 equal 0.05 for one-sided tests, and another series of pages for alpha 2 equal 0.05. So make sure you're referring to the right F tables. Okay, so what we need is the critical values of F. So F critical with alpha 1 equal 0.05 because it's a one-sided test. The degrees of freedom here, so degrees of freedom for the numerator, sample size was 20, so 20 minus 1 is 19. Sample sizes were equal here, so the degrees of freedom for the denominator are the same, so it's 20 minus 1 equals 19. So F critical, alpha 1 equal 0.05 with 19 degrees of freedom for the numerator, 19 for the denominator equals, so if you look that up, I got the value of, it's actually approximately 2.14. And so now we need to, I'll sketch out the F distribution. So again, F distribution looks something like this. Here's 0. Tails off this way. Again, whether we're doing a one-sided or two-sided, we're always looking out at this end. And so here, all alpha 1 equal 0.05 is stuffed at this end of the distribution, and the critical value is approximately 2.14. Our F-calc was 1.86. So where does this sit? It sits over here in the region of non-rejection. So again, we don't reject the null hypothesis. Conclude, no reason to believe males are more variable than female ducks. So no reason to believe males are more variable than females for whatever the trait is we happen to be measuring. It's really a simple test. And again, we're using it in two ways. One, if the experimenter is inherently interested in variability, is this group more variable than that one? Or are there differences in the variability of these two groups? And the other way we're going to use it is we can always, whenever we really want to do a two-sample t-test, before you complete that t-test, test the assumption of homogeneity of variances. And in fact, if you run this in SAS, if you do t-tests in SAS, and you can get the details of how to use SAS for two-sample and paired t-tests from the problem sets, SAS, when you do an independent sample t-test, it will also do for you this F-test to ask whether or not those variances are different. Okay, so let's have a look at the F tables. So here are statistical tables, and I'll come back to the T tables in a moment. So here I've taken only portions of the F tables. So here's the F table, or a tiny portion of it, because this will span many pages. This is one of the, or a portion of the pages of the F distribution for a one-sided test, right? At the top, you see it says alpha 1 equal 0.05. So that's the table you're going to use whenever you do a one-sided F test. So that's the first thing you need to look for. Then, because you have two sets of degrees of freedom, the numerator degrees of freedom are across the top of the table. So for however many degrees of freedom you have, in the numerator, you look across the top of the table. The denominator degrees of freedom are down the side. So I think for that, you'd have to look to another page to find the values for 19. So 19, remember in the test we just did, we had 19 degrees of freedom in the numerator, 19 in the denominator. Those values are actually not even on this table. My denominator here only goes up to 17, and the numerator ones only go to 10. So you need to refer to other tables. But let's imagine we had a case where we had something that had 7 and 7 degrees of freedom. So 7 in the numerator, here's 7. 7 in the denominator, here's 7. So here would be the critical value, 3.79. Right? So it's and the reason these tables span many pages in your text is there are numerator degrees of freedom, denominator degrees of freedom, and different pages for alpha 1 equal 0.05, other pages for alpha 2. So make sure you familiarize yourself with those tables and make sure you're on the right page. You're looking for alpha 1, you're checking for degrees of freedom for numerator and denominator. Okay, so here's another portion that I took of the F tables. This time it's for a two-sided test. Alpha 2 equals 0.05. That's what tells you that's the table you want. And then you use the tables in the same way, right? The numerator degrees of freedom are here, so pick out the appropriate one. The denominator degrees of freedom are here. If you need more degrees of freedom in the numerator, flip to another page that will go to 11 and up, let's say, and then denominator degrees of freedom continuing on. So that's the way in which these F tables are used. And while I'm here looking at stats tables, let me just go back and refresh your memory about the use of T tables, if I can. So here is students' T distribution, or at least a portion of it. So just as a reminder, pertinent to the t-test we did, both the paired t-test and the independent sample t-tests, for T, it's just a single table, but you have different rows for alpha 1 versus alpha 2. So if you're doing a one-sided test, you want alpha 1 equal 0.05. So this is the column that you want to refer to for varying degrees of freedom. Right? And the critical values are here. If it's a two-sided test, alpha 2 equal 0.05, this is the column you want to use for hauling out critical values of T for a two-sided test. So again, make sure you're familiar with the use of these tables so that you don't actually go through the motions, correctly carry out the t-test, Then when you go to the tables, you blow it and draw exactly the wrong conclusion because you're not using the tables correctly. So make sure you know how to use these tables. Become comfortable with their use. Okay, so that really completes our discussion of F-tests, really a test for variances, and we'll proceed on with later on in another lecture what you do if assumptions fail.